Welcome to the lesson on the introduction to the trigonometric functions. In this lesson, we will be introducing the 6 trigonometric functions as defined for an acute angle in a right triangle. This document that I'm working with and that I'm going to be marking up as I go through the lecture is available to you. It's on Blackboard in the Week 1 folder. And you're welcome, or rather it's in the Week 2 folder. You're welcome to download that, and there's some blanks in here you can fill out and assist you in your note-taking if you'd like. All right, we are going to define the 6 trigonometric functions for an acute angle in a right triangle. So what that means is I need to have a right triangle here. I have one. Let's go ahead and mark this angle as the one that is 90 degrees. And I've already marked this angle as the one I'm going to choose to work with for my trig functions. Could you work with this one? Yes, you could. We'll be doing some of that as we go along. Now I'm going to give a name to this angle. It is traditional in trigonometry to use one of a handful of Greek letters for the name of the angle. And this is one that's called theta. And I've given you a little coaching on how to pronounce it here, theta. And the way you should draw it is something like a skinny O, a capital one, with a little cross mark or a crossbar in there. So that's theta, and it means this angle here. All right, now once I've got my angle chosen, I can talk about the 3 sides of the triangle in a pretty simple way. First of all, it's a right triangle, so one side is the hypotenuse, the side that's opposite the 90 degree. I have 2 other sides that in general we call legs, but I'm going to call this side the opposite. You could say the opposite side or the opposite leg because it's at the side opposite of the selected angle. And this one here I'm going to call the adjacent, abbreviated ADJ, because it's adjacent to this, it's next to this angle that I've chosen. And now I'm going to give the definition of the 6 trigonometric functions for this angle theta. Well, they're right down here. And they have names, by the way. They are written out in full here just above: sine, cosine, tangent, cotangent, secant, and cosecant. But typically we don't write out SINE or cotangent, for instance. That's a pretty long. One of them is sine is abbreviated by SIN, cosine by COS, etc. So those are just abbreviations for these long forms of these names. All right, now let's walk through the 6 functions. All of these are simply ratios of the lengths of the side of the triangle. So if I want the sine of theta, I define that to be the opposite divided by the hypotenuse. The cosine is defined to be the adjacent divided by the hypotenuse. The tangent is the length of the opposite divided by the length of the adjacent. And I have 3 more: the cotangent, cosecant, and secant and cosecant. Now, you should memorize these. Of course, in an online course, it's very difficult for me to enforce that, but I'm just giving you my best advice. This will probably not go terribly well, or as well as it could if you don't commit this to memory. However, there are some patterns in this list that can help you tremendously in memorizing, but there are also patterns that are extremely helpful in calculating. So I want you to notice, for instance, that, well, let's pick this middle pair right here, the tangent and the cotangent. The tangent is the length of the opposite side divided by the length of the adjacent side. The cotangent is, well, it's just the reciprocal of that, right? Instead of opposite over adjacent, we have adjacent over opposite. So the cotangent, you could say this: it's equal to 1 over the tangent of theta. And I've already written these reciprocal identities in. The secant is the reciprocal of the cosine, and the cosecant is the reciprocal of the sine. So in other words, if you look at these nested pairs, that pair there, the innermost pair, tangent and cotangent, are reciprocals. The next pair out, the middle pair, the cosine and the secant, are reciprocals, and likewise the sine and the cosecant are also reciprocals. So if we know that sine is opposite over hypotenuse, tangent is adjacent over hypotenuse, and cosine rather is adjacent over hypotenuse, tangent is sine over cosine, then that saves us, that gets us all of the ratios, except we have to flip them all over to get the other three functions. And if you know the order, sine, cosine, tangent, cotangent, secant, cosecant, you will not have any trouble computing these three on the bottom once you know these three on the top. So I recommend that you actually do that. Now, it's all well and good to have this in the abstract, but you know, what does this actually mean? So I'm going to flip this page over, draw a triangle, and I'm going to compute all 6 trig functions, and you'll see how it works. Okay, so suppose we have a right triangle, and this came up actually in the last lesson. We know that the numbers 3, 4, and 5 are a Pythagorean triple. In other words, they are the lengths of the sides of a right triangle. 3 squared is 9, 4 squared is 16, 9 and 16 make 25, and 5 squared is also 25. So there is such a right triangle that has lengths of its sides 3, 4, and 5. I'm going to choose this one and call it theta. I know that I have some bright minds with me, so somebody's going to say, well, how about that? Couldn't you choose that one? Yes, I could, and I would get 6 trig functions for that angle as well. So what I want to do right now is just write these out. The sine, the cosine, and the tangent of theta. I really shouldn't speak in such shorthand. Sine of theta, cosine of theta, tangent of theta. We wouldn't just say squared by itself when we're doing math, right? It's always like x squared or 2 squared. It's something that has to be squared. In the same way, you got to have the sine of something. You got to have the cosine of something, etc. So it's the sine of theta, the cosine of theta, etc. Now, the definition of the sine from the other side of the page is this. It's opposite, means the length of the opposite side over hypotenuse, the length of the hypotenuse, so that's this one, 3 divided by 5. And 3/5 multiply up and down by 10 is the same as 6/10. So 0.6 is the sine of this particular theta here. Cosine of theta is adjacent over hypotenuse. The length of the adjacent is 4. 4 over 5, multiplying up and down by 2, we get 0.8. And finally, I didn't give myself quite enough room. Let's move that down. Tan theta is opposite over adjacent. Yeah, the opposite side has length 3. The adjacent side to theta has length 4, so that's 3/4 or 0.75. Now, there are 3 more. The cotangent, the secant, and the cosecant. I'll get to them in just a minute, but let's just work with these three right now. I want to show you just very quickly why it is that people care about trigonometry, or at least one of the reasons why people care about trigonometry. We know, for instance, that if you have a 30, 60, 90 right triangle, if this were 30 degrees and that were 90 and that were 60, then we know that this side would be half the length of the hypotenuse, and this side would be root 3 over 2 times the length of the hypotenuse. But with a 3, 4, 5, we actually don't have all that information. We know the length of each side, but we know the measure of the right angle, of course, but we don't know the measure of these two acute angles. So how could we get them? Well, I suppose one way would be this. You get a big sheet of paper. You could use some drafting tools that are quite precise and draw this very, very carefully and use a protractor, right? That would give you at least some information about the size of the angle, but it wouldn't be all that precise. It turns out that by using the trig functions and our calculators, we can get extremely accurate estimates of the size of these two acute angles, and I want to show you that right now. So I know this right now, that if you start with the angle theta and take its sine, you will get the number 0.6. Now, if a lot of mathematical operations and functions have inverse operations and inverse functions. So for instance, if my function is to do this, to multiply by 2, so that'd be f of x equals 2x, its inverse function is f of x equals 1/2 x. In other words, if multiplying by 2 gets you the first functional value, then you could divide by 2 to get back to the place you started from, right? So if you start with theta, take its sine and get 0.6, then you could sort of untake the sine, and there's a name for that function. Right now I'll call it the inverse of the sine function. If you take the inverse of the sine function of 0.6, you would get theta. It's the thing that we plugged into sine here. Well, that's what we don't know, right? We don't know exactly what the size of that is. But fortunately, our calculators can give us really accurate estimates. So I'll show you how to do that just real quick here. If I turn on my calculator, and you notice across here, I've got sine, cosine, and tangent. Right above it, I have the inverse of the sine, the inverse of the cosine, and the inverse of the tangent function. So if I press that second button and then inverse sine, I can plug in this 0.6, and what I'm doing is asking the calculator what angle has sine 0.6, and I push equal, and if I were to round that off to a couple decimal places, I'd get 36.87. Theta is approximately 36.87 degrees. Now, I should mention that before you jump in on this, you really want to check a setting on your calculator. The mode button here, press that, and you'll notice I have two choices, angles in radians or angles in degrees. You want the degrees set for now. There will be some times in the courses where we'll definitely use radians as well. But for now, for this problem, degrees is what we want. So there you go. We now know something about this angle, and actually we know about this one here too. The sum of the measures of the angles in a right triangle is 180 degrees. We know that this one is 90 degrees, that's the right angle. We know that this one is approximately 36.87. So if we took the sum, 180 degrees, subtracted off this angle we just computed, then we can subtract off the 90 that we know that we have in the right angle, and we end up with 53.13 approximately. And now I know everything there is to know about that triangle. I know the length of each of its sides, and I know the measure of each one of its angles. These, of course, are approximations, but the calculator is giving me very high accuracy. Probably all of these digits are correct. So using the trigonometric functions, we really can get a lot of information out of triangles. And if you think of it, a lot of complicated diagrams can be decomposed into triangles as well. So we're making real progress when we're able to begin to work with the trigonometric functions.